So now let's go to double replacement reactions. All right. So there are three driving forces for double replacement reactions. Now let me back up a minute about driving forces. There are reactions for which we will not know about driving forces. Okay, there are some reactions that can occur without knowing what these are some like basic driving forces. Okay, you could almost be assured a reaction is going to happen with the driving forces we're talking about. Excuse me, but there are some chemical reactions that will occur even without these driving forces. Okay, but we don't get into that in this class. That makes sense? All right. So let's look at the solubility rules, because that's where we get our driving forces. One of the places we get our driving forces for double replacement reactions. So there are three driving forces. Only one of them has to do with this. Okay? There are three driving forces for double replacement reactions. Only one of those driving forces comes from the solubility rules. Okay, so the three driving forces are, one, the formation of a solid. Well, that's where this comes in. Okay, the formation of a solid. That's what we use this for. And most of the chemical reactions we'll work with that are double replacement reactions, this is what we're going to use to find out if there's a driving force. Okay? Well, a double replacement reaction in our class will be assumed to occur if it has one of these three driving forces. The first one is the formation of a solid. And that's what we're going to use this chart for right here. Okay? The second driving force that's almost as important, is the formation of water. It is just as important for acid-base reactions. Okay? The third driving force, which you will almost never see in this class, is the formation of a gas. You will almost never see that happen in this class. The third driving force is the formation of a gas. Okay? About the only case where we would have the formation of a gas is the one we talked about yesterday, where we form this carbonic acid. Okay? If one of the products is carbonic acid, well, that automatically breaks down into H2O and CO2, and CO2 is going to be a gas. Okay? So the formation of H2CO3, while that doesn't appear immediately to be have a driving force, but since it breaks down automatically, in essence, it does give a driving force to the reaction. Does that make sense? Anybody confused by that? All right, then let's take a look at some reactions. We're only working with reactions at this point that are at room temperature and pressure, so that'll be liquid water. Okay, the only time we're not is when you're doing a combustion reaction. As we said, that creates a lot of heat. Okay? Okay, let's take a look at this reaction. All right, so I have two-part compounds. I have two ionic compounds: potassium fluoride, magnesium chloride. Okay, so if a double replacement reaction is likely to occur, or will occur rather, then the potassium has to go with the chloride. KCl. If it's a double replacement reaction, the front part of this has to go with the back part of that. And the front part remains the front part. And then if a reaction is going to occur, the front part of this has to go with the back part of this. The front part remains the front part still. Okay? Now I haven't balanced either one of these formulas. Okay? I need to balance the formulas. But I'm going to choose to find out if I have a driving force first, because if I don't have a driving force, there's no reason to even do anything else. Okay? So I'm going to look on the solubility rules, and I'm going to first notice that all nitrates, acetates, ammonium, chlorates, perchlorates, and group 1 salts are always soluble. Well, potassium is in group 1, isn't it? So anything that has potassium is always going to be soluble, and if it's soluble, it's always going to be aqueous, dissolved in water. Soluble means dissolved in water. Okay? So soluble is what it'll do, aqueous is what it is. Okay? All right. Magnesium fluoride. Let's see. Well, there's fluorides there. And all fluorides are soluble. All fluorides are soluble except group 2, lead 2, iron 3. Okay? All fluorides are soluble. So all fluorides are aqueous except when fluorine is combined with a group 2 metal, lead 2, or iron. So is this going to be soluble or not? Not soluble, so it's going to be a solid. It's going to precipitate. Okay? All right, so look at the products. Do we have a driving force? Yes, because we formed a solid. That's one of our 3 driving forces. Okay? So now that we have a driving force, we know the reaction will occur, we can balance the equation. What do you use to balance the equation? Atom inventory. Okay? This? I did answer your question. We know it's a solid because it's a fluoride compound. And fluoride compounds are going to be solids if fluorine is combined with a group 2 metal, and that's a group 2 metal. Magnesium is in this second column. That's a group 2 metal. Second column of the periodic table. Do I need to go through a little more detail on it? All right, so here's magnesium. It's in the second column of the periodic table. That makes it a group 2 metal. And so if fluorine is combined with a group 2 metal, everything up here in the top is soluble. That means it's going to be dissolved in water. It can be dissolved in water if there's water around. We know there's water around because we've got these aqueous symbols up here. There has to be water around for it to be dissolved. So this is the state. This is what it is. This is what it can do. So the solubility rules tells you it can dissolve, or it would not dissolve if it's down here. Okay? Up here it tells you it has dissolved if it says aqueous next to it. Does that make sense? So fluorine, if it's combined with a group 2 metal, or if it's combined with lead 2 or iron 3, is going to form a solid. It will not dissolve in water. Not. That's correct. Okay. So we need to be careful about the solubilities rules, folks, okay? These compounds down here under insoluble are not going to dissolve in water. They are going to make solids, but there are exceptions to those. Notice carbonates and phosphates are almost all insoluble. So even in an aqueous solution, they're going to dissolve, they're going to settle to the bottom as a solid, unless those carbonates or phosphates are combined with a group 1 metal or ammonium. Yes?
I don't really understand how to balance the formula.
You don't? Okay. So look on the periodic table with oxidation numbers and tell me the charge on a potassium. And how about the chlorine? Okay. So that's a 1-to-1 ratio, right? That gives me a 0 right there. Okay? What's the charge on magnesium? What's the charge on fluorine? So that's a 2 plus and a 1 negative.
Oh, so you have put a 2 next to 4.
Yes.
That's substitute.
That makes sense?
Yeah.
Okay. Yes. Here? Well, because well, let me say this. It will work out once you balance the equation. You'll use coefficients to balance the equation, and that you'll get enough chlorines. But subscripts only travel when they're part of a polyatomic ion. Hello? Again? Jay Breezy? I mean, he's just like skipping out all the time. Go ahead.
Come on, Josh. Sorry.
I know it. The goose. Okay. All right. You're welcome. All right, you guys. Jay Breezy and the Goose Man. Y'all got to pick up a pass at in the attendance office. Okay. No, when you leave here.
I didn't know if I just saw it.
No, you can't leave my class. I'm sorry. Okay. I did say it on camera, yeah.
Why is everyone howling at the moon?
All right. If you were supposed to leave, you'd leave, but obviously you don't have to. Okay. Where were we? Okay. A simple thing to remember, Molly, if it throws you off a little bit about that is, the only subscripts that travel from one side of the equation to the other. The only subscripts that travel are those that are part of a polyatomic ion. Okay. So really, what you're trying to do is you got to get the formulas to balance first, and then you balance the overall equation with coefficients. Okay. You can't just stick a 2 on there because that would unbalance the formula. So, okay? All right.